Welcome to recitation number 2. This is regarding lecture number 3 with the topic of computing limits by algebra. And I'm gonna have 6 examples today. And if assuming I can make things work properly with Canvas, we are gonna be using this tool that's called Play Pause It, which allows me to give you questions related to the ones that I just solved on screen. This is what's going to be consistent, what's going to be your lecture activity for, recitation activity for this week. We'll see if I can actually make that work. But okay, if you're still confused about the difference between a lecture and a recitation, is that lectures introduce all the new material that you need, whereas recitations are more focused on problem solving, applying the techniques. But that doesn't mean you should skip the recitations, because this is where you get to see how the most common problems are actually solved. So we're going to start with this one, which is the one that I had planned for the lecture, but I skipped it. So we have two limits in here which involve trig functions. For both of these, remember that you should first of all plug in the number x equals 0 in the first case, x equals pi in the second, to see if the denominator is not a 0. But unfortunately, in both cases, it will be a 0. Here, for the second one, you need to know what cosine of pi is and just check it that they are 0. So that means we need to simplify these in some way. And what these problems have in common is that they are about trig functions, and what you need to be doing is replacing them with sines and cosines. That's going to be our strategy. So I encourage you to pause a little and see if you can figure it out. And now I'm going to be solving them. For this first one, the limit, we have a secant, which is 1 over cosine. We should know all these trig functions. And then tangent is sine over cosine. That's the limit in item A. Now we want to essentially try to simplify this. For example, the numerator is a difference involving fractions. We can try to find a common denominator by writing 1 as cosine over cosine, for example. And then once they have a common denominator, you can subtract them like this. This is the numerator. Now this denominator is also a fraction, so I'm going to instead be writing its reciprocal in front of the fraction that we had already. That's how you divide by a fraction. You just multiply by its reciprocal. And you see now that the cosines are going to go away. There is a cancellation here. This leaves you with just cosine of x minus 1 over sine x. And now that a simplification happened, you should try to check whether the thing that we have is actually computable by plugging in 0. And unfortunately, you'll see that it's not. Sine of x is still giving you a 0. Sine of 0 is a 0. So we still need to simplify this in some way. There are a couple things that we can try in here. I'm going to give you one possibility. This is a similar trick to the rationalization when we have square roots. It is going to be possible to do the same thing here by multiplying and dividing with cosine of x plus 1. So anytime you recognize that a trick like that might be helpful, you should try it. If you don't see what else you can try. It's not like there's always just one answer. As long as the simplifications that you're doing make sense mathematically, it is still it can still work or not, but what you're writing is correct. So as we know now, in the numerators, we have cosine minus 1 and then cosine plus 1. When you multiply the two of them together, you have the square of the first minus the square of the second. Meanwhile, the denominator is still sine times cosine plus 1. And let's see how this is going to help us. First of all, usually people don't write it like this, cosine square with the parentheses. If you want to square a sine or a cosine, you usually put the square here in the function name. So it's like cosine square x. But that really doesn't matter. You can still write it as parentheses square. Okay, so, and sure, 1 square is 1. Now what is happening? Remember that we want to get rid of this sign. That's the term that's giving us a problem in the denominator. Somehow we need to make sure a sign appears in the numerator so we can cancel. And what we're going to be using here, you see a cosine squared there. There's no signs. However, you should always remember this fundamental property of trig functions, that sine square plus cosine square is equal to 1. This is the Pythagorean property. So we can actually rewrite cosine square as 1 minus sine square, essentially using this identity to solve for cosine square, to isolate it here. So I'm going to replace cosine square x with 1 minus sine square x. And what happens with that is that because there's also this minus 1 in front, it will get canceled. The 1 will get canceled, and the only thing left will be a sine square, which will cancel the problematic term downstairs. That's all that we needed. So what happens here? 1 minus 1 is 0. Those go away, so the numerator will only have a minus sine square. I can move that minus outside of the limit. You don't have to, but it's good to simplify as much as possible, like that, to clean up the formula. And now you have a sine square above and a sine, just sine below. You can cancel one of those powers. You are still going to have a sine at the top and nothing in the bottom. So what happens? Minus limit sine x over cosine x plus 1. And now finally, this is okay. It is okay now to plug in a 0. Don't forget the minus in front, but then sine of 0 is 0. Cosine of 0 is 1. 0 divided by 2 is 0. So that is the first limit. How do we interpret that? Essentially, those were two functions that were both going to 0. So the limit might actually have any value if it exists. And what ended up happening is that the value was a 0. That means kind of that the function in the top is the one that wins. It's the one that goes to 0 faster than the one in the bottom. Because when you divided one by the other, you still got a 0. Now try to graph this to convince yourself that that's true. Let's move to item B now. I'm just going to copy it down here. I think this was a pi. Cosine x plus 1. Cosine square plus 3 cosine plus 1. Sorry, it was a plus 2 in the end. Okay. What is this one? Again, plugging in pi gives you 0 over 0, which means we need to simplify. This is actually just a ratio between two polynomials, but they're not polynomials of x, they're polynomials of cosine of x, as you can recognize. You can still factor the one in the denominator. It's a quadratic. You can try to find its two roots and factor it out. The two roots here would be when cosine x is equal to 1 or 2. So that means this is just a multiplication of cosine x plus 1 and cosine x plus 2. Distribute this out to see that this is true. So now you probably recognize what we have to do. Cosine x plus 1 appears in both places. We can cancel. Again, the reasoning for this is cosine x plus 1 is only 0 when cosine x is minus 1, which is the case at the number pi. But if you're talking about a limit as x goes to pi, then actually you're looking at values of x close to pi, but not equal to pi. So the expressions they were canceling are not actually equal to 0 when you are around x, when you're talking about a limit. That means you can cancel them. And now that's all you needed, because, well, now because we can plug in. Remember that we had a theorem that says cosine and sine are functions for which you can plug in, as long as the whole expression is not giving you a 0 in the denominator, then you can do that. Cosine of pi is -1 in particular. -1 plus 2 is +1, so this is 1/1, which is a 1. So now in this example, the two functions were going to 0, and when we take the ratio between them, we find a limit of 1. That means that when you're comparing one to the other, you're finding a value 1. They're essentially of the same size. The two functions go to 0 at the same rate, more or less. So this was my example with trig functions. Assuming I can play posit correctly, if you're watching this from the Canvas site, now you'll be able to see a question that you should answer. This is going to be graded automatically, but you'll have unlimited attempts after you watch the video. So let's see if that works. The link should show up now. Okay, now we are moving on to a different type of problem. Take a look at this. X in this case is not the limit variable. X is just a given number. We don't know what it is. And the problem is calculate the following limits in terms of X. If you look at the limits, the limit variable is called age in this case. So whatever answer we have, there will not be an H in it because H is just a limit variable. But there will be X. X is present inside, and so it is just like a fixed number, and it will be present in the end. Now these are they're called difference quotient type of limits. They show up when we study the derivative. That's why we're talking about them now. But for us, the important thing is that these are simply limits that we have to simplify. Look, for example, in the first one, what happens when you plug in age equals 0? Remember that age is the variable, is the limit variable. So it's the one that's going to 0. But the denominator, it would give you a 0. And that's true in both cases. So that's how we know that we need some simplification. And what is the simplification? In the case of item A, it is just computed. You have a difference of fractions. So you should just find a common denominator. Any way you would like to do that. For example, in this case, it would be x times x plus h. So you can, if you rewrite the first fraction, including an x, and then you rewrite the second fraction, including an x plus h, then you're able to now take the difference. They have the same denominator. Again, different people think about sums of fractions in different ways. As long as what you do is correct, you should get to this answer. And what is happening with that, with this whole thing? Well, think of it this way. We have this whole fraction in the numerator, whose numerator is x minus x plus h. The x's will go away. You're only going to be left with a minus h. So this was the fraction that was upstairs here. Now the whole thing is divided by h, so you can write it like that. Multiply by 1 over h. Just so you don't have fractions of fractions. And now you see that the h's will go away. We can cancel them. Leaving us with an expression. Don't forget the minus sign. Okay, what is this now? Again, the variable in the limit is h. That's the one for which we try to plug in 0. And if you try that now, you can see that it works. So I guess one important thing that I forgot to mention in this problem, so I'm going to add it to the problem statement. I just said x was a given number. I should have said something more for both items, actually. For the first one, we're going to assume x is not 0. And for the second one, we're going to assume It's larger than or equal to 0 because of the square root. That's important. That should be in there. And now you can see, okay, it is actually possible to plug in h equals 0 in here. It will not give you a 0 denominator because x is not 0. So we can do that. And what is x times x plus 0? That is just x squared. This is our final answer because they said find an answer involving only x. That was item A. If you're curious, this computation finds the derivative of the function 1 over x. We're going to study this in the near future. Meanwhile, item B is computing the derivative of the square root. Let's look at item B. I'm going to copy it down here. Again, try to do this yourself first. What is the trick here? You have, sorry, the thing going to 0 is not an x. It is actually an h. All right. We have a difference of square roots. And anytime you have a sum or a difference where at least one of the terms is a square root, you should try to multiply and divide by the conjugate, which is just the same expression where you change that that difference into a sum or vice versa. What happens when we do that? Numerator becomes the difference of the squares, and the square of the square root is just the thing inside. So x plus h minus x. Again, you can see this happening if you multiply it out in the numerator. If you distribute everything and cancel, this is going to show up, but you should be familiar with this from algebra. Now, denominator, again, we're going to simply leave it as h times the other expression. Why are we leaving like that? Well, look in the numerator, the x's are going to go away. There is only an h left, which is going to cancel. That's how the problematic term in the denominator goes away. And you're left with a limit where now it is possible to plug in h equals 0. If you put h equals 0, let me just write it very carefully. You have root x plus root x. Sorry, there should not be a limit sign in here anymore because we already plugged in. So just the expression. Root x plus root x is 2 root x. Now, if you were paying attention to when I modified the problem statement, I guess I should not have included the possibility that x is 0. So we would have, I'm going to change this again, x larger than 0. That's the whole point here. If x were equal to 0, then this expression would not actually make sense. We would have to analyze the limit more carefully. It would be a plus infinity. But that's a topic for next lecture. Okay. Moving on to the next example. This is one that involves the absolute value function. And also you see that I had a typo. I had to erase a few of my things and write the number 4. So let's read this. You have a function f of x defined like this. And we're saying it's only defined for numbers larger than or equal to 0 because we're taking a square root of x. And also we're being careful to say only defined also for numbers which are not 4. Because if x is 4, that gives you a denominator of 0. The function would not be defined. But regardless, this function is defined around the number 4 on both sides. So it is defined not at the number 4, and also for numbers larger than or equal to 0. So it is defined in a whole interval around the number 4. That means you can talk about all these limits here. converging to 4 from the right, from the left, and just overall. The question is analyze the limits. How do we do this? The trick is, because there's an absolute value, remember that the absolute value of anything is defined like this. It could be that thing if that thing is larger than or equal to 0. And it is minus that thing if that thing is negative. So if you have a negative y, you put an extra minus in there to make sure it's positive. That's what the absolute value does. So the trick for limits with absolute values is always to try to rewrite them as piecewise defined functions. In the case of the absolute value of x minus 4, that is x minus 4 when x is larger than or equal to 4. Y larger than or equal to 4, because that's the same thing as saying x minus 4 larger than or equal to 0. The thing inside of the absolute value being 0 or more is when the absolute value of the expression is the expression itself. And if not, then it's the negative of that expression, minus x plus 4. Okay, so when x minus 4 is negative, which is the same thing as x less than 4, then that expression becomes that. So that means we have two separate expressions for our function. I'm just going to rewrite the function. It had an absolute value of x minus 4 in the numerator, and then this denominator stays the same, root x minus 2. And it has a different expression if x is less than 4. So it's a piecewise function. And the limits that we're talking about are all at this number 4 where the function changes behavior. So really, this is why they're asking for lateral limits. You cannot, I mean, you have to use one or the other expression depending on which side you're coming from. And the answer for the limit itself is that it's going to exist as long as both of the lateral limits are the same. Otherwise, it does not exist. So we just have to compute those two. Let's start with the right side. If you're coming towards 4 from the right, that means x is larger than 4. So that means you're going to be using this first expression for the function. X minus 4 over root x minus 2. What happens if you plug in 4 here? You have a problem in the denominator. That means you have to simplify this somehow. There are different ways to simplify it. You might, if you're following like a recipe, if you don't see what to do, first thing you should try is multiplying with a conjugate. You have a square root minus 2, so you're going to multiply with square root plus 2. What happens here? Upstairs, we're just going to leave the two terms multiplying each other. There's no reason to distribute them out. Downstairs, root x plus 2 times root x minus 2 is equal to root x squared minus 2 squared. And okay, you see what happens here. X minus 4 will cancel. Leaving only root x plus 2. Now you can plug in 4. And this gives you a value of 4. That's the first limit. Let me move on to the second limit. What happens different in here when you're coming from the left is that now x is less than 4, which means you have to use the second expression for the function f instead of the first. So I'm going to write that in here, but then everything else will be the same. In particular, you can solve this by the same method, or you can just simply realize the difference between this limit now and the one above is that we changed the sign. The numerator has changed sign. I wrote 4 minus x. I guess I had written minus x plus 4. Yeah, that's the same thing, right? Minus x plus 4 or 4 minus x is the same thing. But just let me rewrite this for clarity. So yeah, we're just multiplying by -1. That's the difference between the two. So the answer that you will find is a -4. If you're solving this in an exam, you should absolutely not do this, by the way. You have to actually write what you're doing. If you want to skip steps like this, you can say this is just the limit above with an extra -1. That's fine. But don't just leave steps like this without explaining. But yeah, anyway, we just found the two lateral or one-sided limits, and they are different. So to answer the last one, because the two limits that we found are different, the regular limit of the function does not exist. And that's all. That's all for this example. Next example, here is a piecewise function. They're asking whether the limit at 0 exists. Let's take a look at this function. It's some expression which is a rational function when x is negative. Then it has an absolutely crazy value at the number 0, 42 pi cube. And then for positive x, it is a negative square root. Now they're asking us, does the limit at 0 exist? So the first thing you realize, I mean, that's always true when you see a crazy value, it doesn't have any effect on the problem. The value of the function at the point where you're taking the limit has no relevance. Really, it's just going to be the two functions that give you the value that will affect this limit. What we have to do to answer this question, because it's a piecewise function, it changes behavior on either side of 0. You have no choice. You have to analyze the lateral limits separately and see if they're equal. So we're going to start by doing the right side. On the right of 0, which means x is larger than 0, be careful here. It's the last expression. For x larger than 0, it is the one with the negative square root. And well, there is actually no problem in plugging in x equals 0 here. You can do that. Minus root of 25 plus 2 times 0. So in other words, minus root of 25, which is a -5. When you have a negative sign outside of the square root, it simply means you're taking the negative number whose square is 25 in this case, so -5. Okay, and from the left, let me scroll up. The function was x cubed minus 5x squared divided by just x squared. I'd say this is the simplest type of function where a simplification is needed because, well, yeah, of course we cannot plug in x equals 0 in this way, but this simplification is very clear here, I hope. Namely, if you factor an x squared from the numerator, then the x squares will go away. You're left with just x minus 5, for which you can actually plug in 0. And 0 minus 5 is -5. Now notice that the two answers that we found for the one-sided limits were equal. And we had a theorem that said whenever this happens, the limit is also, it exists and it is that same value, -5. Okay, so what is happening with this function, if you think about its graph, the value at 0 is the crazy number 42 pi cube, wherever that is. That's irrelevant. But both of the functions on the left and on the right are converging to the number -5. On the right side, it is this negative square root function. So it's going down, something like that. And on the other side, it's some rational function that you can try to understand what it is. Let's see, this would be like x minus 5. So some linear function, actually. Just so you can visualize what this function is doing. It's two different curves, but they're joining at the same number. One x is 0, so that means there is a limit. Moving on to the next problem. These are a bunch of trig functions. What we're going to be using for these guys are the two important limits that we ended the last recitation, the last lecture with. Sine x over x as x goes to 0, this is important, the 0 here, is a 1. And cosine minus 1 over x is a 0. The ones that we should always remember. But they are going to be used in here, but not directly. For example, if you look at item A, here's what you should not do. You should not say that sine of 4x is equal to 4 sine x. Absolutely not. That's not true. There is an actual expression for sine of 4x if you use the double angle formula twice. It's just ugly. We don't want to do that. There's something simpler that we can do here. If you want to try to think about the trick, you're welcome to try so, but it's kind of a hard trick if you haven't seen it already. So it's a fun puzzle for you. But the answer is, well, if we had a 4x, the thing inside of sine is 4x. If we also had a 4x in the denominator, then that would be of the same form here. It's limit of sine of some variable divided by that same variable as that variable goes to 0. It's just that that variable will be 4x now. So it would be very good for us to have a 4 downstairs. But we cannot just modify the function like that. If you want a 4 downstairs, you must also have 1 upstairs. That doesn't change your limit. So we can do that. Multiply by 4 over 4 doesn't change the function. And now you do have the useful thing. This 4 can be brought outside of the limit. We don't care about that one. And now the limit that you have inside is sine of 4x over, well, 4x is what you have downstairs. Let me circle that in green maybe. So now, as I said, when x is going to 0, the variable 4 times x is also going to 0. So this is what's called a change of variable in the limit. You have now sine of something divided by that same thing, and that thing is going to 0. This formula here, the reminder that I just gave you, is telling us that this goes to a 1. So you can write that as 4 times 1, which is 4. So we'll do another example after this one about changes of variables like this to consolidate it. But for these examples, all you have to know is basically that, for example, in this formula right here, you can, instead of x, you can have anything that also goes to 0 in place of x, and it's the same limit. So the answer here is a 4. Now let's take a look at the second one. You have sine of 2x over sine of 3x. This is also a 0 over 0 if you plug in. So you know a simplification needs to happen. And unfortunately, unless you know a formula for the triple angle for sine, there's not much you can do here. And if you ask me, I don't even know that formula from the top of my head. It's not very common. But instead, the trick is, again, if we could have somehow a 2x in the denominator, that would be very helpful because sine of 2x over 2x would be going to 1. And also, if we could have a 3x in the numerator, that would be good. 3x over sine of 3x would also go to 1. I mean, sine x over x goes to 1. So if you flip it, it goes to 1 over 1, which is 1. So, okay, we actually want to have a 3x upstairs and a 2x downstairs. That would be very helpful. But we can only do that if we then also cancel it out. So this is the trick here. We are multiplying by 1. right? 3x and the 2x here, they're going to cancel each other. So it's fine to multiply by this whole expression here, which is a 1. But what we want to do here is now do some simplification, some rewriting. First of all, I'm going to cancel these x's with each other and move the 2/3 to the front. This is a 2/3 that's left, it goes outside. And now the other things that are left inside of the limit, you have a sine of 2x over 2x. And then you also have a 3x over sine of 3x. Now we're basically done. If you look at the expression inside of the limit, this one, it's a multiplication of two functions, and both of them have a limit. Remember, this is the law of multiplication. Limit of the product is the product of the limits, provided both exist. So we can do that. Limit of sine of 2x over 2x times limit of 3x divided by sine of 3x. And now this is just the thing that I had mentioned. When x goes to 0, 2x also goes to 0. And because of that fundamental limit involving sines, this is a 1. Now the next one is just the reverse of that. It will give you the reverse answer, which is 1 over 1. And the answer is 2/3. Take your calculators, try to do this. Take a very small number x. Make sure it's in radians, although it doesn't really matter because we're taking it to 0. But compute sine of 2x divided by sine of 3x. If x is really, really small, you will find a number really close to 2/3, the limit. And the last one here, 1 minus secant over x. Again, first thing we try is plugging in, but there's an x in the denominator, that's bad. Now, if that doesn't work, what we have to do is simplify. And if you see trig functions which are not sine or cosine, try to replace them with sines and cosines. In the case here, a secant is a 1 over cosine. Now take a common denominator in the top. However you like to do that. 1 is cosine minus cosine. And now you can take this difference of the two fractions in the numerator. The denominator is cosine x, and then another x in the denominator. All right, so this was the simplification. Although nothing canceled so far. There is nothing that we can cancel here. Certainly not the cosine with the cosine, because there is a sum here or a difference also. So no. But what do we recognize? Here's the thing now. If you try to write this, then you are wrong. Don't write this because I'm going to erase it. You might want to try this. But that's very bad. Remember, the limit of the product is the product of the limits as long as both exist. And if you try to analyze, in particular this one here, you will see that it does not exist. 1 over x as x approaches 0 is a case where we're going to study it's a limit that's plus infinity from one side, minus infinity from the other. So it's not a number. That means you cannot split it like that. I have to say this because I know this mistake shows up a lot. But what we can do is recognize two different functions that are multiplied together and they have limits. This guy and, well, just what is left is 1 over cosine. Right, so I'm actually taking the cosine x minus 1 divided by x. That's my first function. And the other one that's left is 1 over cosine. Those are two functions which are multiplied together in this expression. And now, provided that both of these limits exist and are numbers, then I can do this. And in fact, they will exist. The first one we recognize is almost the one of the fundamental limits. Let me scroll back up. It's that one with the cosine. Cosine of x minus 1 goes divided by x goes to 0. This one is just 1 minus, well, actually, it is exactly that one. Sorry. I thought it would be the negative of that, which would also be 0, but it's exactly the same. So that's even better. Cosine x minus 1 over x, as x goes to 0, just goes to 0. What about the other one? Well, cosine of 0 is 1, so you can plug in. There are no problems plugging in. So as I said, both of these limits actually exist as numbers, and one times the other is going to be a 0. So you can do that. Now the final example for today. Compute the following limit. This is one where we're going to be using this change of variable. Remember that the fundamental limit involving sine is sine x over x, which is a 1, as long as x is going to 0. The limit that we have in here looks a lot like it. It's sine of an expression divided by some expression, but x is not even going to 0. It's going to minus 3. However, we recognize that when x goes to minus 3, both of the things inside of the sine and outside here are also going to 0. So this looks very much like a sine of something that goes to 0 divided by something that goes to 0. We want to make sure that we can use that. And the way to do that is a change of variable in limits. We haven't explicitly talked about it in lecture. However, it is very simple. When you have a linear expression like this, a multiple of x plus or minus some number, you can always make that a new limit variable. You can call that whatever you want. For example, y is your new variable. And it's also useful to have the reverse change. Maybe you want to need that later. Essentially, try to solve for x in terms of y here. If you subtract a 6 and divide by 2, that's x in terms of y. But what's also important to understand is what happens to the limit. As x approaches minus 3, where does y go? And you write it as x goes to minus 3. Y goes to, well, because it's just a simple linear expression, you plug in the value minus 3 for x, and you find what that gives you for y. And as we had remarked, it gives you a 0. So what that means is that you can now rewrite your original limit in terms of x using the variable y. But the limit changes. As x goes to minus 3, y goes to 0. Now the thing upstairs, 6 plus 2x, is precisely the thing that we had called y. That's why we're doing this change of variable. The one downstairs, if you look at it, you may recognize immediately it's y over 2. Right? 3 plus x is just half of this expression that gives you the y. But if you don't recognize that, you can always just use the formula for x in terms of y that we found up there. So let me do it that way. Plugging in the formula for x in terms of y. And now you can try to simplify this to see that just a y over 2 is what shows up. This is basically 6 plus y minus 6 over 2. So I'm going to multiply by the reciprocal of this fraction. There's a 2 upstairs, and then 6 minus 6 is 0. Just a y is left. So as I said, the expression was y over 2. And what we do with this limit, the 2 can go outside. Where you have left is sine of y over y. As y goes to 0, this is the fundamental limit with the sign. It is equal to 1. And the 2 makes it a 2. So pay attention to this type of limit problem as well, where you can change a variable, change a limit variable using some linear expression. And also some more general expressions are possible, but linear ones are the ones that you see the most. When you have a variable going somewhere and you recognize that it would be more useful to consider a whole expression as some other variable, then you can do that. And as long as you understand where this other variable goes to, like here.